Bronsted-Lowry acids and bases. This definition is going to be very similar to the Arrhenius definition that we had earlier, except that we're going to acknowledge that there are no free protons in solution. So instead of an acid releasing a proton, it donates one to another compound. And the base is going to accept a proton. That's a little different than the Arrhenius made hydroxy. But here a base will be anything that accepts this hydrogen ion. Okay, so what we get is if we have a free proton in solution, it will combine with water to make a hydronium ion. And a neutralization reaction looks more like this. We have an acid, this is hydrochloric acid, and it's going to react with water, which in this case is going to be a base. So the acid is going to donate a hydrogen ion, and the base will accept. So when water accepts a hydrogen, it becomes this hydronium. And when the acid donates, we get this chloride ion. So what we have here are pairs. Let's look at a new reaction, and we can see how we have a conjugate acid-base pair. We start with ammonia, NH3. On the other side of the reaction, it's an NH4 ion. We start with water. On the other side of the reaction, it's a hydroxy. So the ammonia here goes from NH3 to NH4, so it must be the base, because it's accepting a hydrogen. The water is losing a hydrogen, losing a proton, and so it is acting as our acid. We can also, on the other side, label the conjugate acid and the conjugate base. So here's the base, the ammonia, and over here we have the ammonium ion. They would call this the conjugate acid, and this is the conjugate base. So the base is associated with the conjugate acid, and the acid is associated with the conjugate base. You can see if you ran the reaction in the opposite direction, and you can see that it is reversible, that the acid would indeed be giving away a proton, and the base would indeed be accepting a proton. Water is called, it is notably noted for being amphoteric, and that just means that it can act as a base or an acid. So it can act as a base or as an acid. It can accept a proton or it can donate it. It depends on the company that it's with and its environment. So let's label these two reactions that we have below us as acids and bases, and conjugate acids and conjugate bases. So we probably want to first figure out which ones are paired. So let's change my color here. This hydrofluoric acid is going to be paired with the fluorine ion there. And the water will be paired with the hydronium ion here. The only difference between the hydrofluoric acid and the fluoride ion is that it's minus a proton, and so this is our acid because it's donated its proton, it's lost its proton. This will be our base because water has 2 protons here and the hydronium on the other side has 3 protons. So if hydrofluoric acid is our acid, then our conjugate base must be here. The conjugate base, if we go the other direction, acts as a base and accepts hydrogen to make hydrofluoric acid. And the hydronium ion here is our conjugate acid. And so water is acting as a base. So let's look at the other one. We've actually already looked at this one once, so we'll look at it quickly. Let's first line up our pairs. The NH3 is going to be paired up with the NH4 that's missing its positive sign. It's an ion. And the water this time is going to be hooked up with the hydronium. With the hydroxy. Here we have a base because on the other side of the reaction it has another hydrogen. And then that leaves our water as our acid. The acid is connected to the conjugate base on this side, and this must be then the conjugate acid. So on each side we have an acid and a base. On each side we have a conjugate acid and a conjugate base. Note that the base is attached to the conjugate acid. So let's look and identify some pairs here. So here we have HI, I'll just call it that. And we're going to first figure out what it goes with on the other side. And I think it goes with this iodine ion. And the water then must go with the hydronium. So water is gaining a hydrogen as it goes across the reaction. So it must be our base, leaving the this acid as our acid. This is our conjugate base, and this would be our conjugate acid. See? So look and see how they're, which groups you can put with which groups, and then see whether they've gained or lost a hydrogen as they've in the reaction. So the fluoride ion here gains a hydrogen, so it's accepting it must be a base. That means this has to be an acid because we have to have an acid and base on each side. This must be the conjugate acid, and this must be the conjugate base. So let's look at the next one. It's a little more complicated, but we can still do the same thing. We're going to figure out what our acid-base pairs are. Those two will go together. The only difference is that this one has an extra proton that this one does not have. So it has lost a proton, so it must be an acid. We can look at this other compound, change colors. The only difference here is that here we have 2 hydrogens, and here we've got 3 hydrogens. So this has gained a hydrogen, so it must be the base. We can see which ones are connected to each other. If this is the base, then its pair on the other side must be the conjugate acid. And this leaves us with this being the conjugate base. We can also just write at conjugate bases. So if these are our acids, the conjugate base of this is going to be this compound minus that proton, minus that H. So it'll be a fluoride ion. The conjugate base of water is water without one of its protons, so that would make it a hydroxy. And if we lose a hydrogen here, we end up with PO3. So each time we've just removed a hydrogen to write the conjugate base. Now if we want to write the conjugate acid, we're going to add a hydrogen. So we'll add a hydrogen to our carbonate here and we're going to take away one of our negative charges because we're adding a positive charge with the hydrogen. Hydronium ion, and again we have to add the positive charge because we're adding a positive ion. And we'll do the same thing here to our phosphate. And we've lost all our negative charges. No longer an ion. All right, so next we'll look at the strengths of acids and bases.